Okay, so this talk is about the Grothendieck-Lefschetz trace formula and the implication of the Weil conjectures except for the Riemann hypothesis, which will be done in the remaining of the workshop. And in this area, there are a lot of confusing ideas and definitions, like a lot of them, but some of the confusion comes from linear algebra and some of the confusion comes from algebraic geometry. So I will try to give like a non-standard presentation of this by starting with something completely in linear algebra and doing an analog over sets instead of over schemes. And then I will move on to do it like over schemes. And I hope that this will make it easier to digest. So first of all, we will start over a point. So this is the first part. And let V be a finite dimensional vector space and equipped with a linear operator. This will later be the Frobenius that Segev just told us about. And we define the L function of this data of V with phi by the characteristic polynomial with the somewhat non-standard normalization. So if AI are the eigenvalues, this is 1 minus A1t all the way to 1 minus ANT. So this is just the characteristic polynomial. This is what the L function is. And the first lemma is something that Tomer already explained in some way, is that we can rewrite this as the exponent of the sum over R from 0 to infinity of the trace of the map T to the R over R. And let's do this. It is very easy. So we know that the Taylor series of minus log 1 minus t is this. And if you write phi as an upper triangular matrix with the eigenvalues on the diagonal, then you immediately see that the eigenvalues raised to the power n or kr if you raise the map to the power r. And if we take log of the L function, then by this description, you get that it is the sum of minus log 1 minus AIT. And now we use the Taylor series. And now we just rearrange to get what we needed. And this part is, of course, the trace of phi to the r. Okay, so this is a result completely in linear algebra. This basically finishes what I wanted to say about the case of a point, but let me also introduce a notation to simplify our life. So if G, I will write sheaves and chain complexes with G rather than F because I don't write F so nicely. And if G is a bounded chain complex, and it has of finite dimensional vector spaces like before, and we have a phi from G to G. And in this case, I will denote the trace of phi acting on G, or my pen stopped working. Sorry, I will quickly try to fix it. Okay. And I will also denote this sometimes by phi acting on the cohomology. Then I define this to be just the sum with signs on the individual cohomologies. So like for me, the trace on the chain complex is the trace on the cohomologies with the appropriate sign. And similarly, the determinant I will denote in the same way, but this is a multiplicative thing. So we need to multiply and put the sign as a power. Okay, so this is, sorry. So this is just a notation. And evidently, everything I did before, all these things, you can define and run the same proofs for such phi over acting on G instead of on V. Okay, so now let's move to the second part, doing it over a set. So let X bar be a finite set. In a moment, I will actually say that we don't need it to be really finite, with an endomorphism, F, which will later be the Frobenius, from X bar to X bar. We denote.
Maybe I'll just make a very short remark that your definition of a trace of a complex is also
Categorical trace.
The categorical trace. It's you don't have to ad hoc define. It's the correct definition.
Exactly. And my pen stopped working again. I hope this is the last time. If not, I will move on to the notes. So we define X. Let me try one last thing before I'm moving to explaining it with the notes. Sorry about the technical problems with my pen. Does it work? No. Okay, so my pen doesn't work. I will have to move on to the notes. Sorry about that.
If you prefer, you can talk and I will write what you're saying.
I think it will be okay with the notes, but thanks. Okay, so can you all see my PDF?
Yeah.
Okay, so about the technical problem. So as I started to say, we define X bar F to the R, sorry, here, as the fixed point of F to the R. And since I assume that X bar is finite, then every point is fixed by some power, but we don't really need to assume that it is finite. All we need is that each of those is finite and that the union is all of X bar. And for every X in X bar, we define the degree dx as the minimal number under which it is a fixed point of F. And we define the closed points of X bar, maybe it should be of X, but X does not exist, as the quotient, the orbit. And for each such orbit, of course, we have dx lifts to X bar itself, and they are fixed by F to the R if and only if dx divides R. And so there are zero lifts if it is other than if dx does not divide R. Okay, so now I define a sheaf on X bar, and I recall that in this case, X bar is equipped with this map F, and a sheaf on this is just a family of finite dimensional vector spaces, one for each point, and together with a map phi from the pullback of V to V itself. So this means that I have a map from V f of x to Vx for every point x. In this case, for every point, which is fixed by f to the r, we get a morphism from Vf to the r x, then you can apply phi to get a map to Vf to the r minus 1, and all the way to Vx, so you apply it r times. And the first one is Vx, because I assume that x is fixed by f to the r. And I denote this map by phi x to the r. Also, For x tilde, we denote by the horrible notation, which I will follow because this is the standard notation in algebraic geometry. Phi x tilde is like you choose one of those lifts x, and you define it as phi x to the dx, to the minimal degree. So this is like the minimal degree you need to have such an endomorphism. And of course, this definition depends on x because Vx is like an abstract vector space, but it only depends on the x up to isomorphism. And therefore, in particular, the eigenvalues do not depend on the choice. And if we have a map between sets with an endomorphism, so that make the corresponding diagram commute, and we have a sheaf W on Y, then we define the pullback by pulling back. So we define a sheaf on X by the value at X is W f of X. It should be f of X here. I changed all the P to f at some point. And we similarly define the push forward of a sheaf on X by summing along the fibers. So again, it should be f of X equals Y of V of X. And now I define the sheaf to function correspondence. So let's say that I have a sheaf over X bar. Then we define the function TRV, which is a function on the points fixed by f to the r, by taking the trace of the corresponding Frobenius on the point. Okay? I hope that everyone is with me. And
can you repeat this last thing?
Yes. So I have this sheaf V over X bar, and I want to define a function on the points fixed by f to the r. And if I have a point, then by what I said here, I have an endomorphism of this point of V of X, which I denoted by phi x to the r. And I can just compute its trace, which is a number. It's a number in the field, the algebraic closure of the field over which the vector space is defined. So it will be Q bar if V is over Q, but you can do a version over any field and take the algebraic closure.
Cool. Thanks.
Okay. So this is what I will call the shift to function correspondence. For a morphism from f to x bar to y bar, we can pull back a function. So if we have a general function, it doesn't have to come from such a thing, but this would be a case. If you have a function here, you can just pull it back by applying f to x. And similarly, you can push forward by taking the sum on fibers. So you sum over all, so the value at y of the push forward is the sum over all fibers x. And a very easy observation is that for f, a morphism, the f upper star commutes with p to the r. So taking this operation just commutes, and this is just because both are defined by evaluating the point at the target. Okay, and here is the Janowski trace formula, which is called this way because Lior suggested this whole formalism over sets. So if we have a map, then also the push forward commutes with t to the r. Okay, and in this case, this is an easy theorem. It's not as hard as the Grothendieck-Lefschetz trace formula, and it follows by the fact that trace takes direct sums to sums. Okay. And let's see an example. So if we have a map to a point, and V is the constant one-dimensional with phi being the identity on X, so we just, on every point we put Q, for example, or whatever the field of definition is, then the sum of traces, which is like applying F lower Schrick to T to R, TR of V, this would be easier if I could write it, but applying this to V, then you just take the trace of the identity because phi is the identity over X bar. So it just gives you the number of points. And on the other hand, we can push forward the sheaf, which gives us this morphism and take its trace. And this equality is obvious in this case, but later we will have something more sophisticated. Okay, So now I want to define the L function of such a sheaf. If I have a sheaf, I will take every point, which is like every orbit, every closed point. I will look at the Frobenius del, the phi of x tilde, and I will take the L function of this with t normalized with the degree of x tilde. So this is just a definition, and it is this, okay? So this is what happens if you open up the definition of L. And here is a proposition, which I don't think it really helps to explain step by step, but you can use the description we had as an exponent also for this. So what we get is that you can rewrite this not as a product over the closed points, like the orbits by the action, but over all the points. So you go over all r and you go over all points fixed by f to the r, and then you sum the traces and put the correct weight. And this is a very easy exercise. You just use the fact that for every closed point, there are dx lifts if and only if r is divisible by dx. Okay, so this is very easy. I think it won't help if I will explain it. If you want to read the proof, it's written here. Any questions so far? Okay, so since we had the Janowski trace formula for TR, and this thing is exactly the P lower shriek of the F lower shriek of TR, then it implies that if we have a morphism from X bar to Y bar, and we have V, a sheaf on X bar, then the L function of X bar Vt is the L function of Y bar of the push forward. Okay, so in particular for Y bar, we get that the L function of X tilde is just the determinant of the push forward of V to a point. So now this is a single vector space, not over many points, because there is only one point in Y bar. And we have the induced Frobenius on it, and you just take the determinant, and this is the definition of the L function in this case. And note that what the Janowski trace formula does is like a global, local to global kind of a thing, because this thing was defined as a product over the closed points, while this thing is defined using like summing all the different vector space, which is like a global thing.
Shay, just to make sure, so earlier you said that X can be infinite as long as all stabilizers have finite index or something.
Yes,
Here you actually need the
point
sets to be finite, right?
What you need is that the map from X to Y will have finite fibers.
Yeah, sure, okay.
Okay, thanks. Yeah, I didn't think this through. And if you replace V by a chain complex G, then everything generalizes, I think. I think there should be no problem. And now,
wait, I don't know why we need finite fibers.
I don't want to spend too much time about
okay,
it.
fine.
This is not like this is not the way things.
Okay,
are.
no, never mind.
Okay.
You have finite products in the formula. This is just.
Yeah.
Before we go on, I just want to say that just about the set thing, I suggest if somebody wants to kind of get a better feeling of what's going on, like that this is not it's a very, very simple situation, but it's not vacuous. Okay, so if you have just a permutation of a finite set, you can consider the matrix permutation of it. You might wonder what is the characteristic polynomial of it in terms of the cycle structure of the permutation. Of course, it's an easy exercise in computing determinants, but this formalism gives you a description of the characteristic polynomial as a product of 1 minus t to the d, where d is the size of the cycle over the cycles, without computing determinants explicitly. This kind of thing you can get from this type of formula. It's just a simple exercise I suggest for anyone who wants to get a feeling of what actually achieved in this mechanism.
Thanks. So let's move on to the case of schemes. So throughout, we will consider schemes defined over FQ, which are of finite type. So let X be such a scheme. and let x bar be the base change to the algebraic closure. And I recall from Segev's talk that this x bar is equipped with a geometric Frobenius and other types of Frobenius. And this satisfies that if you have a point over FQ bar, then it is fixed by the Frobenius to the R if and only if it is defined already over FQR. Okay, and if we have a point, and then there is a minimal dx such that it is defined over FQ to the dx, and this is the minimal number such that it is fixed by this. So this is very similar to what we had in the set case. And the closed points are, well, the usual definition of a closed point is like a speck of a field living inside X. And in this case, this just means that it is like, okay, I will say it differently. So this is the definition of a closed point. And if we have such a closed point, it should be X tilde here and here. Then you can choose, there are many, but you can choose an isomorphism to FQ to the DX. And each one of those will give you a map. Each such isomorphism will give you a map from spec FQ to the DX to X, which is an FQ to the DX point. So this gives you DX different lifts to a points here. Why DX? Because we are over FQ. So this is the number of automorphisms of this. So this is the number of ways you can take an isomorphism between these fields. And so this also is very similar to what we have with sets. And now recall that if we have G, chain complex of sheaves, I will already assume that it is constructible, which is, this is the way I denote this category, but for what I'm saying now, you don't need it. Then, as Segev explained to us, we get a phi from the pullback of G bar to G bar. And therefore, if we have a point which is defined over FQ to the R, then by applying this morphism R times, we get again a map F phi X to the R from the stock at this point to itself. Okay, so for example, if R equals 1, then as we heard before, this is isomorphic to G bar, and then you get just a map phi X. But if X is defined over FQ to the R, then you really need to take this map to the power of R, or at least to the minimal times, such that this map factors through FQ to the DX. And again, if X tilde is a closed point, we define phi X tilde as phi X to the DX. And as I said before, this is very analogous to what we had with the case of a set. So the set X bar now is replaced by the scheme, and the morphism is replaced by the Frobenius, and the relationship with points, like closed points and the points themselves, is also very similar. And over a sheaf, and if we have a sheaf over X, then we get a sheaf over X tilde with such a morphism, which is what we had before. Okay, and now we can define the shift to function correspondence in this situation by exactly the same definition. So if we have G defined over X, then we define TRG. It's a function on the points, on the FQ to the R points. And we just take the trace of the Frobenius acting on the base change shift at this stock. Okay, so same definition from before. And once more, we can define the pullback, and we can define the push forward by the same formula. So you just, the pullback, you just apply to the point, and the push forward, you sum over the fibers. And okay, so here's one example. Let's say that Y is spec FQ, then Y has a single point at FQ to the R for every R. so that TRG in this case, it's a function from a point to QL, so you can just think of it as an element in QL, and this element is the trace because the sheaf is just over one point. And it is also very easy to see that if you have a point in X, an FQ to the R point, then its value at X, it's the same thing as if you take TR to the G and you pull it back using this formula, then it is, and apply this. This is also all very clear. And if you apply this formula for Gx, then again, you get the same thing. So all of these three things coincide. And another example is that if you take the map where Y is again spec FQ, then what F-Lower-Schrick TRG is, it's just the sum of traces of the Frobenius on the stocks. Okay, because the sum here is over the fiber, but the fiber of the single point is everything, all X FQR, so you sum all points at FQR. Okay, questions about this?
So what you are describing now is a mechanism to take the local information in the stocks and relate it to the global information, which will lead us to the formula of the traces and the Lefschetz blah blah.
Yes,
right?
exactly. This is like the next theorem is about computation of F-Lower-Schrick with T to the R. So like this is a formalism which encodes all the traces as a function, and therefore you can sum all of those things in different ways, like for different maps from X to different Y's. And this is exactly, as you say, will lead us to the Grothendieck-Lefschetz trace formula. But before that, I will just say that it is very easy to see that it commutes with pullback. Again, this is like completely obvious because it's just the value at a single point. So one quick way to see it is that you need to prove that that if you apply this to G, like to a single complex, and you apply it to a single point X, then the two functions coincide. So you need to show that this is equal to this. But an easy way to prove it without even opening the formula is using the fact that, as I said before, TRGX, you can calculate it by pulling back to X tilde. And so this means that like to X. So if you just use this and use the fact that this would be F, that you can take them, pull back to a point under T to the R, this follows immediately. But it's also very easy from the formula itself. Okay, and now here is the Grothendieck-Lefschetz trace formula, at least one version of it. It says that if you have a separated morphism of schemes of finite type, F from X to Y, then the F tilde commutes, F-Lower-Schrick commutes with T to the R. And I remind you that this is just the summation over the fiber. And this is like really the push forward of sheaves. So this thing is much, much more complicated than what we had in the case of sets. In the case of sets, this was just a direct sum. For sheaves, you know, it's an infinity functor between infinity categories. It is a complicated thing. So this theorem, it is not obvious. It's not the kind of thing that you get immediately by replacing traces with direct sums or something like this. This is a hard theorem, and I will discuss it in the end of the talk. For now, let's just assume it and see how we draw a lot of conclusions from it.
Let's just emphasize though that your F-Lower-Schrick on the right, it's usually denoted by R F-Lower-Schrick. It's a derived function.
Yes, like capital R F-Lower-Schrick. Not this R, the R of like right derived functors.
Whereas, why is it in the left it is not derived or something like that?
Because it's just a functor of, like it's a map of sets. It's this thing. It's between sets. It's not infinity categories.
It also acts on functions. How do you do a derived function? A derived functor which takes a function to a function?
It's not a functor.
Yeah, it's not a functor.
functions.
you can't derive your
The map.
functions, but
Yeah.
f lower shriek is like the derived function. I denote all things are the derived automatically. I will not write write derived function.
Yeah.
Okay, so one special case is that if you take f to be the morphism to the point, so y equals spec fq, then what this side gives you, so this is like the formula for the value at a single x, and the f lower shriek gives you the sum. And on the other hand, this f lower shriek applied to G, its cohomology is exactly the compactly supported cohomology of G. And here we get the trace of the Frobenius. So as you can see, this can't be trivial. Like, it's not a direct sum, it's a cohomology, it is a complicated thing. And if you apply it to the constant sheaf QL, then the traces here are simply the identity, because the Frobenius acts trivially on the constant sheaf. So this is the trace of the identity, which is 1. So this side just becomes the size of this, because you sum 1 this many times. And on this side, G is QL, so you just get the cohomology. So this allows you to count points using this mechanism. And I gave this example yesterday in the Q&A, but I think it is very worth our time. So let me say it again. So let's take X to be the projective space over FQ. And there is the standard decomposition as Pn minus 1 and the affine line. This is like a union where the intersection is trivial, but it's not like a disjoint union. It's not a coproduct. So in this way, you see inductively that like this contributes Q to the n points over FQ. And then you get inductively this formula for the number of points. So this is like one way to compute this side. And additionally, I think we didn't do the computation, but you can show that the cohomology of Pn, it is like the cohomology of the complex projective space in topology. So it is concentrated in even degrees from 0 to 2n. So it's 0 to 4 and so on until 2n. And then it is also like the projective space in topology. It is one-dimensional with the coefficients QL. But here we also have a Tate-Twist. Did we talk about Tate-Twist at some point?
I don't think so, but I will talk about it talk about it in my next talk.
Okay, so Leo will talk about it more, but basically what it means is that the Frobenius, like if the Frobenius acts on a Tate-Twist by Q to the I, so Leo explained it better than I do. But this means that the eigenvalues, there is a single eigenvalue, like we act on a one-dimensional vector space with a scalar. So this scalar is the trace, it's Q to the I, and therefore the trace on the cohomology, which I remind you I defined, or it is the categorical trace, it is just the sum of the traces on the different cohomologies with signs, but we are in even degrees, so all of the signs are plus, and therefore you get 1 plus Q plus all the way to Q to the n. So as you can see, in this case, the formula holds, and it is much more general than this, of course. Okay, so now I will define.
I want to make a very slight remark.
Thank you. Okay.
Which is that Pn is smooth and proper. So what we should expect, according to the more important, the Weil conjecture in the form that we want to prove, is that the size of the eigenvalues acting on the cohomology in degree k has absolute value Q to the k divided by 2. And first of all, this is exactly what you see. You see that the eigenvalue at 2i is Q to the I, which has absolute value Q to the I. So that's the first observation. The second observation is that once you know the full strength of the Weil conjecture, even if you happen to not know how to compute the cohomology of Pn, because you missed algebraic topology, you can use this formula to know what the cohomology has to be, because you see that it's a sum of geometric sequences. Each of them, each of them has a absolute value q to the I from 0 to n. So it has to be one-dimensional cohomologies in degree 0 all the way to n.
Right.
So it allows you to compute the cohomology.
You assume that you know the size, like the number of points, and
Yeah. I assume that I know the number of points in the projective space. That's a very easy computation.
Yeah.
And there are actually cases in which this is a useful way to compute cohomology of money.
Yeah, so I think a nice exercise, which I also learned from Tomer, is that you can also compute the cohomology of the Grassmannian using the same kind of technique, because it is easy to count points of the Grassmannian. And by the comparison theorem with singular cohomology, it actually tells you the cohomology of the Grassmannian over the complex numbers, the actual compact topological space with singular cohomology. So it's very
Really cool.
easy and nice.
Really cool. Okay, so now let's define the L function of the sheaf. So we define it again using the local L functions. So the L function of x and g t is the product. It's exactly the same formula. You take the product over closed points of the Frobenius and t normalized with the correct degree. So this is again just the determinant of 1 minus t to the dx tilde phi x tilde. And let me also remind you that this thing is like choosing a lift x and then taking phi x to the dx. Okay? And exactly the same proof, word to word, proves that you can rewrite this as an exponent and summing not over closed points, but over like the fq to the r points. Okay, so it's literally the same proof. And now, if we again apply the Grothendieck-Lefschetz using this description, we get that if we have a morphism f from x to y, then the L function of xgt is the L function of y and the push forward of gt. And in particular, if you take y to be the point, then we get that you can compute the L function, which was defined as a product of determinants over the closed points, as the determinant of a single morphism acting on the cohomology. So once more, this is a local to global kind of a thing. We compute the L function, which is defined as this, sometimes it's called Euler product over all the closed points, and you compute it via a global thing. So like the cohomology, which sees the global information of X bar. Okay, any questions about this before I move on to the implication of the Weil conjectures? Okay, so the Weil conjectures will assume more about X. I don't know if you really need all of the assumptions, but this is what Bat wrote, so I will copy it word to word. Let X be a geometrically connected, smooth and projective variety of dimension n. And as we know, we are interested in the number of fq to the r points, and we encode them in the zeta function, which is this exponent. And using the fact that if you take
Geometrically connected is connected when base change to the
algebraic closure. Exactly. Thank you.
Mm-hmm.
So if you take the trivial sheaf QL, then the trace at each point is 1. So it counts. So this formula here, will be this number will be 1. So if you put in this the constant sheaf, then you get that the zeta function is the L function of the constant sheaf. So this is what like the relationship between zeta functions and L functions is. And now if you apply the Grothendieck-Lefschetz trace formula as I just said it, like the last version we had here, and you apply it in this case, and since the X we assumed it is projective, it's proper, then the compactly supported cohomology and the cohomology coincide, like F lower Schrick and F lower star coincide. So you get that the zeta function is the determinant of the single morphism acting on the cohomology, which is the compactly supported cohomology. And let me remind you that this determinant is defined as the product with signs, and also note that there is a -1 here. So it is the product with signs of some polynomials, like with polynomials, the HIs. Okay. So it's a product of some polynomials. So it's a rational function, which is the first of the Weil conjectures. Okay.
So far, by the way, you didn't use any of these assumptions. You only assume the text is separate.
We use the fact that it is proper to like identify the
Oh yeah, okay. If you replace this H with HC.
Yeah, you can naturally generalize it this way. Yeah, so now let me restate the Weil conjectures, just so we have them in front of our eyes. And I will also state the Riemann hypothesis, although we will not prove it in this talk.
Shay, can I ask a small question?
Yes, of course.
Are the PI actually like rational? Like, do the polynomials PI actually have rational coefficients, or do you?
They have integer coefficients.
Well,
Integer.
They have actually integer coefficients, independent of L.
Actually, I don't see how it follows from
And
this though. Like the numbers could be in QL.
yeah, how do you see this?
So in general, it doesn't follow from just the. I mean, the fact that the product is a rational function is a function like power series with rational coefficients. It just follows because the zeta function, the left-hand side is. This is. But this is true for every, like Thomas said, this doesn't use this smooth and properness assumptions. And in fact, as far as I know, it is not known that the polynomials have rational coefficients in this generality.
Don't you know that it is like a power series with coefficients in Q? So it's like in the intersection. So the coefficients are in Q.
Yes, but you don't know it in general for the individual polynomials PI.
Yeah,
if you don't know if X is not, if you don't know that if X is not assumed to be smooth and proper. And in fact, it's not known even that their coefficients don't depend on L. But in the situation of the Weil conjecture, Theorem 28, when you do assume that X is smooth and proper, you also have the Riemann hypothesis. The Riemann hypothesis tells you that those alpha ij's are actually algebraic numbers. So, I mean, it depends on how do you phrase them, but the thing you prove that under any embedding of QL in the complex numbers, the absolute value of those alpha ij's is q to the power of I over 2. And like Tomer told us yesterday, this actually implies that they're algebraic numbers and therefore their minimal polynomials are. So that's how you do it.
Cool. Yeah, thanks.
Thank you. Thank you for the question.
It's more obvious, right? Because Z is like a rational function, but it has rational coefficients. So
there's integer coefficients actually.
What? Okay. Yes. Integers, it's more complicated. Yes, I agree.
Okay, so
thanks, Leo. Yeah, that's
I just want to I'm going to say more about it in my last lecture, but I just want to say one thing to emphasize to what extent it is not known. It is not even known for something which is not smooth and proper that the dimensions of the Eladic homology are the same for everything.
Okay.
Something that we kind of, it's supposed to be singular cohomology. It should be the same number, but it's not known in general.
Okay, so let me state the Weil conjecture. So the first one says that the zeta function is a rational function. The second one states that you can know the value at 1 over t, or if you like, put a q to the n here. So the value at 1 over q to the n t is related to the value at t by some coefficient, which is a power of q and the power of t involving the Euler characteristic. And here the Euler characteristic will really be like the Euler characteristic of the étale cohomology. And we also have the Riemann hypothesis, which tells us that the eigenvalues have absolute value q to the I over 2 for each embedding. So I will not discuss it at all. because we're not going to put it now. So the Grothendieck-Lefschetz trace formula already admits it as a rational function, as I said here, and as Leo explained, the Riemann hypothesis will prove that this is a rational function over Q and not over QL. And now for the functional equation, this is essentially, it follows from the Poincare duality. I think we didn't really discuss Poincare duality yesterday, except for in the, well, Asaf explained us how it follows from six-functor formalism, and we did it again at the Q&A session, but let me say very quickly that the idea is that you just, like in the proper case, you know that the lower shrieks and the lower stars agree, and you also know that the dualizing sheaf, which is like the special pullback, that's what it's called, like P upper shriek of the coefficient of QL, it is an invertible object, and it is, and the dualization using it gives you like that the dual of this is this, or maybe this. So some of those things coincide, and then everything else coincides because you're proper. Okay. So this is the way you prove Poincare duality, and the minus n here, should it be minus n? Yes, it should be minus n. This is again the Tate twist, the thing that changes only the way Frobenius acts, but doesn't change the vector space itself. Okay, so in particular, if you apply this, then you get that the dimension of hi is the same as the dimension of h2n minus I, and I denote the dimensions by beta, like Betty numbers. And the fact that this is a dual and that you have a Tate twist also tell you the relationship with between the eigenvalues. So if you have an eigenvalue of hi, then the eigenvalue at h2n minus I, by the fact that it is a dual, you get the inverse, and the fact that you have a minus n Tate twist gives you this q to the n. And now you can just plug in this, for a specific polynomial, pi, and you just open up the value of alpha ij by this formula. You rearrange it and take this product outside. So you get the polynomial times t to the power beta I with the correct sign, and also the product of all of the eigenvalues. And there is also the sign here, which I didn't record because we don't care about it in the, we don't know, like here we know the sign, but we won't know the sign in a moment, so I will not carry it around. So now using the fact that the eigenvalues match, like this eigenvalue times this eigenvalue without the inverse, like alpha ij times alpha 2n minus ij, you get that it is exactly q to the n. So this, and the fact that if you write chi for the alternating sum of the dimensions, the Euler characteristic, then you immediately get this as a consequence. So all of those in the product cancel out together to give you the q and chi over 2, and the t clearly gives you t to the chi. Okay, so this is the way.
Just two quick remarks.
Yeah.
The first one is that this plus minus, it's not mysterious. It's the dimension of something like is the dimension of the middle cohomology even or odd or something like that. It's just, it's not like there's a mysterious sign here. We know what it is. From this formula you can count. It's the number of eigenvalues. Mode 2. My other remark is that this is an instance of using the fact that the Poincare duality is an instance of using the fact that cohomology has the structure of a ring by the cup product, right? And you get a non-degenerate multiplication. But the entire cup product structure needs to preserve the Frobenius action. So this is, you can get more information about the eigenvalues if you know the cup product structure. In particular, if we go back to the example that Shay gave before with Pn, you know that the cohomology of Pn is a polynomial ring, truncated polynomial ring generated by something in degree h2. So the moment that you know that the Frobenius acts with eigenvalue q on h2, you also immediately know that it has to act by q to the I or in h to I, because the map has to respect the couple. Okay, so the structure of the cohomological structure has to respect all the eigenvalues. And the Poincare duality is just one instance of that.
Cool. Okay, so now let's return to the Grothendieck-Lefschetz trace formula. So let me remind you our definition. So if we have a sheaf G, a chain complex G, then we define TRG, which is a function of the FQ to the R points of X. It should be G here, sorry, I changed the notation. Then the value at X is defined as the trace of the Frobenius raised to the R. And the Grothendieck-Lefschetz trace formula says that if F is a separated morphism, and then the F lower Schrick commutes with T to the R. Okay, so first, let's note that if you take if you prove the case of R equals 1, then this implies all of the other cases, because you can replace Q by Q to the R. You didn't use the fact that Q is not a special number. And you can also base change all of your schemes from FQ to the R, and then it follows. It's like the same theorem. So we only need the case of R equals 1. And what are the steps of the proof? So the first thing is to reduce it to the absolute case, so that F is not to arbitrary Y, but to spec FQ, the structure morphism of X. And this is very, very easy. It follows from proper base change. I wrote it before, and if I knew beforehand that it is going to be with my PDF, then I will just display the proof because it's really easy to see. But it just follows from proper base change and the fact that upper Schricks commute with T to T, which is T1, R equals 1. And you just take like a single point in the target, so you have a
Shay, just a small remark. By proper base change here, you really mean not necessarily proper base change, right? In the sense of you take lower Schrick, but the map is not assumed to be proper.
Yes, exactly. So you take like a point in Y, and then you have XY, like the pullback of Y goes to Y and X goes to Y, and you call this map I, and you also have the induced F between XY and Y, which is like the absolute case. And then you use the base change theorem, which tells you that you can switch the maps in such a pullback diagram, and this follows immediately. So for example, this is the power of defining TR, because in most places, this theorem is proven for the sum of the traces or for the L functions, and then you need to like run a spectral sequence argument, or you sometimes have to do something slightly complicated, and if you do it in this way, it is completely obvious. So this is one of the ingenuity of the Grothendieck shift to function correspondence. Okay, the next step, I don't completely understand, so if anyone can say something about the algebraic geometry, I will be glad, but you reduce it to curves. So let me first say how you do it and what is the missing point that I don't know how to do. So you take your X, and then you decompose it to an open U, and it's closed complement Z, okay? And then there is the thing that I don't understand, which is that you can always find a U such that you have a map to Y of lower dimension and the fibers which are curves. This is the part that I don't know how to explain, but let me first finish the argument given this. So if you run an Noetherian induction, then you know that if you do this operation now on Z and you keep doing it, then in the end, you will, infinitely many steps, you will reach the empty set, or it's trivial. So by a Noetherian induction, it will be true for Z. And if you induce on the dimension, then you know it is true for Y. And by the assumption that it is true for curves, we know it for each fiber of this map. So like for every point Y, you have UY, which is a curve mapping to the point Y. And using this, you get it for U. this is the same proof like this that you can reduce to the fibers and knowing it to the base. And then it is also true for X, because if it is true for U and Z, then all the counts just agree by the standard cofiber sequence that relates, it should be G here, sorry for the case, the standard relationship between the sheaf on Z and U and the sheaf on X. Okay, so does someone want to say something about why there exists such a decomposition?
There does not exist such a decomposition verbatim, but you can always find an open subset such as the map from X to Y factors through a composition of such things. Basically,
No, Y is not the one from X to Y. We have only X now.
Yes, you choose one.
So it's not a normalization, we'll just do it, no?
oh yeah, okay, fine.
No, it's not nether. Well, okay, you can think about it as a like you can net normalization and then reducing one dimension. That's one way.
Yeah.
I don't know what meta normalization is.
So every affine algebraic variety has a map to an affine space of the same dimension with finite fibers.
Okay.
I think you can think of it intuitively as if you think about equations, which is not usually the thing that people do, then you can have a parameterization where you fix some of the variables and then you get the solutions are sort of fibered over that. So
yeah, so here are two intuitive ways to think about it. So one thing is that let's say you have 7 variables and 5 equations, right? So your thing is 2-dimensional, okay? In kind of generic, right? You can just what did I say? I said 7 variables, right? So so you can fix one of the variables, right? You can project one of the variables. Project to A1, which is just give me the value of this variable. For every choice of this variable, you are now left with 6 variables and 5 equations. So it's going to be generically 1-dimensional. It's not true that it's going to be there like this everywhere. Maybe your equation has some kind of a condition between them, but generically in an open set, it's going to be fine. So you just fix some of your variables, such that and then the rest have the suspected dimension. That's the algebraic way.
So it's like generic smoothness all around, right? Like all the.
It's not exactly smoothness, but it's very similar in the idea. It's the fact that generically it's the same idea as generic smoothness. You don't get if you have some independence, then it's generic, and maybe things are dependent in a smaller locus, but. So that's the kind of algebraic perspective. You can also give it geometric. Yes.
Yeah, and things can go wrong. So, for example, you have what are called blowups, where you actually the map is 1-to-1 from X to Y, but there is one fiber which is a projective line. So stuff happens, but not generically again.
Yes.
Yeah, and that's the point.
Exactly. So one way to think about it is that algebra tells you that generically the expected number of solutions is as the dimension you would expect. That's one way. If you prefer a more geometric perspective, that's also possible. You can think that you can do the following exercise. You can embed your algebraic object inside high-dimensional projective variety, a projective space. Okay, and so again, let's say your thing is a surface, okay, and you embed it in some, and let's say you embed it in some high-dimensional projective space, and now you can fix a bunch of points outside of your variety in general position, such that so the number of points is such that if you try to put a hyperplane through them, it's going to have codimension but I'm a little bit confused with the numbers. But the point is that you can.
I say it intersects your surface in dimension 0. Think.
You can make it so no, you don't want it to intersect in dimension 0. The thing that you want now is you want the fibers to be one-dimensional. So the thing that you're going to do is you're going to make it so that for every point you're going to choose, if you add it to your collection of points and move a hyperplane, it's going to have codimension 1. So it's going to cut a curve. So one way to get a lot of curves on your variety is take something of codimension n-1 when your variety of dimension n, and just move with those kinds of hyperplanes on it. That's another way that you can get a family parameterizations of curves on your variety. That's the more geometric way. It's important to note, by the way, that this method, right? So we're going to use it again, proving the Riemann part of the story. So again, there was some phenomena that we've seen for smooth and proper varieties, or we want to prove for smooth and proper variety. We generalize it enough, so it should be true for arbitrary maps of varieties and arbitrary shifts. But then we're doing exactly those kinds of geometric maneuvers to reduce to the case of a curve. And in fact, in the Weil thing, we also went to reduce to the case of A1.
Yeah, I can add that historically, Grothendieck started practicing this stuff in his proof of the Grothendieck-Riemann Roch, which again, he reduced to actually like the thumb isomorphism via, to actually just an embedding and then a map of the total space of the vector space into the base. So these kind of maneuvers, yeah, they're applied a lot. So Grothendieck sort of proves everything relative. He really loves that because it actually simplifies for him because he has a lot of this, and then he uses these maneuvers to reduce to simplified cases.
Okay, thank you for the comment. And now we reduced it to the case of a curve, but the shift was still arbitrary. And the next reduction is to reduce it to the case of a smooth curve and the shift being QL. So I didn't dig too deeply into this case because it involves a lot of steps and we don't have time for them. But the idea is that you can again decompose it like here to open and closed parts. So you can take an open part where your curve is smooth and then take the rest, which is just points, and you directly prove it for the points, and then you will reduce to the smooth parts, and then you can decompose it further using the same method into parts where the shift is not only constructible, but where it is really locally constant, and then you you find a natal cover over which it is really constant, not just locally constant, and then you reduce to the case of QL. Okay, and then the last part is really proving this. So you have a smooth curve with k equals q to the L, and I won't have enough time to really explain how you really prove it, but let me say something which is, again, a generalization, but in a different way. So in the end, we're reduced to showing this for f from a curve to spec fq. And if you see what this means for QL, then it is just the sum of those traces should be equal to the number of points, because this is the trace of the trivial action on this should be the cohomology. And so yeah, this is what I meant. So the number of points, because the trace of QL is 1, so the left-hand side becomes this number, and the right-hand side is the trace on the cohomology. So XFQ is the fixed point of the Frobenius on X. And in fact, you can prove a more general theorem than this. And this is very similar to the topological Lefschetz trace formula. So let me first recall this version. If M is a closed, and I think also oriented, which I didn't write, and manifold, and you have some self-map, then you can consider the manifold M times M. and it has two submanifolds. One of them is the graph of the identity, which is the diagonal, and the other is the graph of f. By graph, I just mean, x comma f of x. And the graph is a manifold by itself, and therefore you get an induced map like this because you have a map from the graph to m times z. It's a submanifold, and it also has what is called a fundamental class in the homology. So you get a class in the middle homology of m times m. M times m is 2 m-dimensional, and you get something in hm. And then you have the same thing for f equals the identity, which is the diagonal. So you have these two classes in Hn, and then you can consider the intersection number, which is just using Poincare duality, move to the cohomology and take the cup product. If you want, you can move back to homology at 0, but it's the same. So you get something in Q. So from these two classes, you can produce a number which computes some kind of intersection number. In some cases, it's really a number. I will say something about it in a moment. And let M be such a manifold, and F, this should be F from M to M be as above. Then the intersection number is the trace of F acting on the cohomology. Again, here I mean the sum of the traces with a sign according to the dimension. And in particular, if F has only finitely many fixed points, then the intersection number, as Tomer explained to us, is you can compute it by considering all the fixed points of M, because there are only finitely many of them, this sum will be finite, and then you need to compute the index at the point, and this computes the intersection number. And in the algebra geometric setting, you can prove an analogous theorem, which is like completely analogous and general. It's not only the case of the Frobenius. The hard part there is to define the classes in the middle cohomology of x bar times x bar, and to show that they satisfy similar formal properties to the case in topology. Like you have some properties with the projection to M and all these kind of things. And if everything is smooth, then it is actually very easy. But in the more general case, you need to develop some theory. And once you do this, you can apply exactly the same proof from topology, like literally word to word, and you get exactly the same kind of a theorem. You get that the intersection number is the trace of the Frobenius on the étale cohomology. And in particular, if you take, if your x comes from xfq, and f is the geometric Frobenius, then it has finitely many fixed points. We know what they are. They are exactly this, and this is finite because we assume that it is a finite type. And in this case, it is also very easy to see by directly inspecting the tangent spaces that the Frobenius is transversal to the identity. So all of the indices are just 1. So this side is just the intersection of the two things, its size. So it is the number of points fixed by the Frobenius, and it is computed by the trace as we needed. And I think I will stop here.
Thank you.